All right, good evening. Calc 2 here. So we're going to just talk about chapter 12.5. I'm just going to do two problems here. Okay, this is just going to be number 6, number 7, because they have probability distributions in them. I know you haven't seen them before, and you're just going to walk through it. Okay. So if you want to do this, sorry about that. If you want to do this on your own, okay, I recommend pause the video, maybe fast forward a little bit till you get to a part where you get stuck, and then pick it back up, and then we can go from there. Okay, so recommendation is not just to follow me to do it, but to try to do it on your own. But if you're like, why do they do that? I will try to be answering those questions as we go. Okay, so we're talking about infant mortality. It's a sad thing. Hopefully relatively rare, and we're going to describe it by a Poisson distribution. Okay, the fish distribution if you speak French. Okay, and what we're going to be doing is, what this is explaining is a finite number of occurrences, discrete number of occurrences, so 1, 2, 3, etc., over a continuous medium. Okay, so things that Poisson is used for, number of deaths per 1,000 births. You say, wait a minute, this is not a continuous medium. Like, you're right, it isn't. But we are going to have decimal places in here, so it's going to seem like it's continuous, even though we know it's not. Okay. Most of the time, these things are done with like number of flaws per square foot. So if you're making fabric, it's like number of defects or number of flaws per square foot of fabric. I think I wrote a problem, which is like number of police cars per mile. I think mine was like per 10 miles or something, but either way, it's length is a continuous medium, number of police cars is finite. So we're going to say, okay, there's 0, 1, 2, 3, etc. police cars per mile. Okay. So that's the kind of thing that's used for, is a counted number divided by a continuous medium. Like distance, time would be, right, would be a continuous medium. So like number of births per year would be, well, that would be too big of a number, but number of births per day kind of a thing. Okay, so that's the kind of thing we're looking at. Okay, now lambda, that's what this is. Okay, we will see during the problem that lambda x has a special meaning. The x, that's 0, 1, 2, 3, ... is the events that happen. Okay, and then e to the negative lambda, that's again e to a negative parameter. You'll see what's going on. One of the things that we have to deal with is that all the probabilities in a distribution have to add up to 1. Now, if it's a discrete distribution, we get to do this part. Poisson is a discrete distribution because x is 0, 1, 2, 3, ... If it is not a discrete distribution, like say x is the amount of time it takes for the bus to come, okay, then we use this kind of sum. Okay, so we'll have our f of x dx, and we'll calculate that way. When it integrates out, it has to equal 1. When it sums out, it has to equal 1. All right, so that's not too bad. So the first thing they want us to do is like, well, prove that this thing equals 1. Okay, so we have our Poisson distribution. This is lambda to the x, e to the negative lambda, divided by x factorial. Okay, so I'm just going to break this apart a little bit and just group them a little bit differently. So this is going to be lambda to the x over x factorial times e to the negative lambda. The sum part is going to be dealing with x's because that's the part that goes 0, 1, 2, 3. The e to the lambda part, that is not going to matter for our sums because e to the negative lambda, we're not adding up over it. It's going to be in each value, but we're not adding up into this piece here. Okay, this is just going to multiply through every term. So one of the things that people do when you have a sum, and this is the best advice I have for you for this, is we're just going to start writing it out. So when x equals 0, right, we're going to have lambda to the 0 over 0 factorial plus lambda to the 1 factorial. This is x equals 1. And x equals 2, we have lambda squared over 2 factorial. Sorry about that. I wish I could change this. Plus lambda to the 3 factorial, lambda to the 4 factorial, plus dot, dot, dot. What we're kind of hoping that you're going to do here, okay, is understand or make the connection like, wait a minute, this looks kind of familiar. E to the x was equal to x to the 0 over 0 factorial plus x to the 1 over 1 factorial plus x to the 2 over 2 factorial plus x to the 3 over 3 factorial plus dot, dot, dot. What if the same thing worked with lambda? So this is going to be e to the lambda when we all sum it out of the way out, right? This is the Taylor series that we spent some time on, okay? So the Taylor series for e to the x, if I replace the x by lambdas, is going to be the Taylor series for e to the lambda, okay? So what's going to happen with this f of x business here, okay? When I go ahead and multiply all this stuff out, x equals 0 to infinity of lambda to the x over x factorial times, and this is e to the negative lambda. This piece here is the Taylor series for e to the lambda, so we're going to say, oh, this is e to the lambda times e to the negative lambda. When the bases are the same, we add the exponents, so this is e to the 0, which is 1. Okay, so, hey, look at that. The probability distribution all adds up to 1. Hooray, it's a probability distribution. So when we would say, like, is it going to work? This is the deficit with online homework, because they don't really expect you to break that out and say, hey, I'll bet this is a series I've seen before. They want you to kind of say, well, what's the closest value here? Okay, so here we see an e to the negative lambda, and then we can see, oh, lambda to the x over x factorial, just like we just did, okay? And they want you to make the connection like this is e to the lambda here times e to the negative lambda. That is going to be our pathway to solve this thing, okay? And then they're going to say, hey, note the first n terms, continue. Okay, the first n terms goes to e to the lambda. So just the stuff in the parentheses above, they just want this piece. Okay, I know it's a little confusing, but that was e to the lambda. And again, we did this on the paper like that. Okay, so we can say that, great. And then substitute the expression, this thing, right? And this is e to the lambda times e to the negative lambda. And again, we just did this, okay, but on paper rather than this multiple choice mess. Okay, so I'm sorry that, this is how they do it. This is why we did not choose this book for another class, because you're supposed to do this on your own. But, it's the best of the, well, I should say it's the best. It's what we can manage in a bad situation. Okay, so doing this by multiple choice is not your best bet, but this is what we have. But on the other hand, they should guide you a little bit, because this is a question with a lot of different parts, and you haven't been told to do this, nor do they give you good examples or anything like that. So they should leave you a trail of breadcrumbs, like, we want you to go from here to there. And they lead you with a couple little signposts along the way. So it's not like it's a horrible thing and it's multiple choice, but it's a thing. Okay, so we have a distribution here. Great. Now we want to know what the expected value is. Okay, and the expected value, again, for all distributions, if it's discrete, they want x times f of x from x equals the whole range. Okay, if x can only go up to 20, then this would obviously be 20. Okay, but they just want this to be the whole thing. If it's a continuous distribution, they want integral x f of x, and again, from negative infinity to positive infinity. So I guess what's coming back is improper integrals. Okay, and these have to these will always come out to be the expected value of x, which is the mean. This will come out to be the expected value of x, which is the mean. Okay, so it just depends. Is it a discrete variable? Is it a continuous variable? Usually in classes like this, we deal with continuous variables, mostly because these are kind of hard, but we're trying to reinforce integration, and this is usually what we do with it. Okay, but this is a real thing. Okay, so we're going to go ahead and we're going to sum this up. Okay, so we're going to sum up x times f of x. So we're going to go ahead and we're going to go, well, this is x times lambda to the x over x factorial times e to the negative x. And again, we're just going to pull this to the side because this doesn't have any x's in it. We're not summing anything here. So this is e to the negative x, sum x, x, and then x factorial. Let's type in a couple of numbers. Okay, so this is going to be e to the negative lambda, and then we're going to have 0 times lambda to the 0 over 0 factorial. Okay, delightful. 1 lambda to the 1 over 1 factorial. 2 lambda squared over 2 factorial. 3 lambda cubed, 3 factorial. Lambda to the 4th, 4 factorial. Lambda to the 5th, 5 factorial, plus 6 lambda to the 6 factorial, plus dot dot dot. I just wanted to leave enough there to get a pattern, okay? Because the first, this is not a good pattern. 1 is hard to see anything. 2 will be like and then 3, 4, 5, and 6. These might be we actually might be able to see a pattern. Okay, so I'll start with 3. Okay, this is 3 over 3 factorial. So this is n. This is 3 over 3 factorial. 3 is 3 times 2 times 1 divided by 3. That's going to cancel. Okay, so what we're going to have here, okay, instead of x factorial, all right, so let's go see what happens here. This is going to be 4 over 4 times 3 times 2 times 1. So it's like 3 factorial. 5 would be 5 over 5 times 4 times 3 times 2 times 1. So this is going to be 4 factorial. So let's go ahead and see if we can't write this down. So this is going to be x minus 1 over lambda to the x plus x to the n, and then this is factorial. Okay, this is going to be x minus 1 factorial. Okay, because we took this part out. Okay, and I'm looking at these x minus n's, and I'm like, that's almost what I want. You know, if this was an x minus 1, these would match again, and we'd be able to go through and do our Taylor series again. So what I'm going to do, okay, is we're going to have x to the 5, I'm sorry, lambda to the 5 over 4 factorial. If I took one of these lambdas out, okay, if I made it look like this, x or lambda times lambda to the 4th over 4 factorial, this would be lambda times lambda cubed 3 factorial, right? This would be lambda squared over 2 factorial, and I'd have a lambda there, because it should be 3, right? This should be 3 factorial, but it's not. We're going to make it 2. Notice that each of these have a lambda. So what's going to happen here is we're going to have lambda times, and this is lambda to the n minus or x minus 1 divided by x minus 1 factorial. It doesn't really matter where we start. If x starts at 1, notice we get the same, right? If x starts at 1, right, we're going to get the same idea here. Okay, so still get lambda to the 0 over 0 factorial, lambda to the 1 over 1 factorial, lambda to the 2 over 2 factorial, dot, dot, dot. So what's going to happen here is this piece here, okay, this piece here, this is again going to turn into e to the lambda, we have a lambda here, times e to the negative lambda from the beginning parts of this thing. So again, these are going to cancel and we end up getting lambda. Okay, so x f of x, okay, for x equals 0 off to infinity is going to equal to lambda. This is the average, okay? This is the expected value of x. This is the average, okay? So the average of the Poisson distribution happens to be lambda. So if they told you the average first, we would replace the lambda with whatever that would be, okay? We wouldn't have to worry about going through x's and just confusing you with a bunch of lambdas, okay? So there we go. So yeah, our expected value here happens to be lambda, right? So there we go. Let's check our answer. Say, hey, it's fantastic. Okay. In 2010, the infant mortality rate in a specific country was estimated to be at 6.35 per 1,000 births. Assuming the expected value for the Poisson distribution, find the probability that in a random sample of 1,000 births, there are fewer than 4 infant mortalities. So this is fewer than 4 per 1,000 births. Okay. So let's see if there's a particular hospital that's doing a good job. Okay. So let's see here. We want to calculate the expected value. Oh, no, we don't. We want to calculate the probability. Okay. And that's going to be, those are the hard part for statistics. Okay. They wanted fewer than 4. If you've taken statistics, I'm sure you have recurring nightmares about this. It's like, did they want 4? They want 5? They want 2? What are they asking for? What numbers are less than 4? 0, 1, 2, and 3. Is 4 less than 4? No. So not 4. We want 0, 1, 2, 3. Okay. And what are we doing here? We want fewer than 4 cases. Okay, that's always positive. Okay. So all we're going to do is we're going to add up because 0 is less than 4, or 1, or 2, or 3. So we have to calculate each one of these. All right. And then do not round until the final answer. Okay, that's different from the other problem we do. But do not round until we get to the final answer. So let's go ahead and do that. So what was my average? My lambda was, here, lambda was 6.35. Okay, and we're just going to go through and write this stuff down. So we have a to the negative, right, 6.35 times, okay? Now we're going to have 6.35 to the 0 divided by 0 factorial. That's the 0 one. We have 6.35 raised to the 1 over 1 factorial plus 6.35 squared over 2 factorial plus 6.35 cubed over 3 factorial. Oh, that's right. I think they lied to us on the instructions. I think they wanted 4 decimal places in each one, and then to add them up. Okay, I think that's what they wanted. But we'll go ahead and calculate it that way. That's what I'll type in, but otherwise I'll type in the end as well. Okay, and we'll just see. So what happens is I'm going to distribute this 6e to the negative 635 to each one of these values. So we can actually go ahead and calculate this. Okay, so we'll just make a little chart. 0, 1, 2, 3. It's not big enough. Okay, so I know I wrote bigger than that. Okay, this is like, this is what I imagine that labs are still like for you guys. I don't know if labs are like this anymore. But when I took chemistry, this is very reminiscent of a chemistry lab problem. 0, 1, 2, and 3. Okay, and I'm just going to be calculating these. That's it. So the first one's pretty easy, right? 6.35 raised to the 0 power is 1 divided by 1. So this is just going to be, I'm going to go to 4 decimal places for each and every one of these. So this is going to be e to the negative, you have to use this one, 6.35. Okay, and I only know this because I've gone through this problem several times. And every time I get it wrong, and it's like, you should only go to 4 decimal places. That's not what you said in the instructions. So 0.0017. Okay, 0.0017. Okay, now we're just going to type in the next one. And we're just going to go through the whole thing. And I'm sorry, I don't know how to speed this up and do editing and be nice about it. Okay, so 6.35 to the 1's power times second function ln. So please feel free to go through and fast forward this. Okay, just gonna go on about things and calculate this stuff. Okay, 0.011 to 4 decimal places. That looks like it's going to be a 1. So 0.0. Okay, and oops, wrong one. I don't want that. Come on. Come on. I want you to be up. Okay, calculator, please. Okay, 0.111. Okay, it's like accounting. Okay, trying to make sure I get all my things in the right rows here. Okay, so this is going to be 6.35, 6.35 squared, right, divided by 2 factorial, right, that's not so bad, times second function, ln, negative 6.35, all right. So that's 0.035, looks like a 2 there, so 0.0, and come on, 0.52, or 352, sorry, 352. Okay, and then thankfully we're going to be at the end here because we only have to go down to 3. So this is going to be 6.35 caret 3. 3 factorial is 3 times 2 times 1, that's 6. Okay, and then times second function ln. I probably could have been better about that, but negative 6.35. Okay, and we're going to have this one. So this is 0.0745. So yeah, 0.07. What was the rest of that? 745. All right, and now we're just going to add these guys up. All right, so we have 0.0017 plus 0.0111 plus 0.0352 plus 0.0745. All right, 0.1225. By the way, if you get a probability of something bigger than 1, you know you messed up. Because probabilities must be between 0 and 1 inclusive. It's to be okay to get 1, but if you end up with like a 1.2, you screwed up. Okay, so we have to go back and take a look at what's going on with that. Okay, and we all do. All right, we all do. So it's not like you're a bad and wrong person. It's like, well, you got to go back and check your calculator again because yeah. So that's 0.1225. Okay. And cross my fingers, hoping for the best. And say, one here, check answer. Hey, nope. By the way, this problem has been notoriously wrong for me in a lot of different ways. Sometimes they used a different lambda than they told me that they were going to use. So if you're not getting the right answers on this, okay, there might be a very good reason as to why you're not getting the right answers. Okay, 6.37, okay, 6.35. And I've done this problem enough times to know to say, what did you exactly want me to do? Yeah. Okay, and we'll final check it. All right. got that one. I got that one. Dot, dot, dot. Oh, 1, 2, 2, 6. So in this case, I should not have rounded where I did. Okay, so if you watch this before you do it, thank you, and do not round until the very end. Okay, so I apologize for that, but these have been, yeah, it's been an interesting day with this. All right, and that's all they wanted. That's what they wanted us to do. So we're going to go ahead. We're going to do a similar question. So in a board game, okay, each player takes turns pressing a popper. Okay, if you were played a lot of board games when you were a kid, these were the board games that had like a little plastic thing that you pressed, and it rolled. It was a spring, and the die got rolled inside the popper. Because if you have played enough games with little kids, they'll realize that they could just put the dice in their one hand and it slam. Oh, look at that! I got exactly what I wanted. Like, yeah, no kidding. So this is a way of keeping kids from cheating. Okay, much fewer fights, much fewer times that the board gets thrown off the table. Okay, so they have to roll. Okay, you must pop a 5 or a 4 on the die. Okay, so it's one of those games where you can't start until you get through the entrance requirements. Okay, so if you get a 5 or a 4, the probabilities plus 4s are pluses. Okay, so the probability of rolling a 5 on a die is 1 out of 6. Probability of rolling a 4, 1 out of 6. This is 2 out of 6, or 1/3. Okay, so our f of x is equal to p. I always write this differently. I always write this with the p in front, and then 1 minus p to the x minus 1. Okay, let's just put the p out in front. And they say, well, that's the probability of success. Okay, is 1/3. They're telling us that the mean, okay, is 1 over 1/3, which is going to be, right, 1 divided by 1/3, which is 3. Okay, so there we go. All right, so that's our average. All right, so chances are you won 3 times before you get to start the game. I'm sure that's delightful. Expected value, complete the parts A, B, and C. Using the expected value for F, what is the expected number of times a popper must be pressed before a success occurs? That's going to be 3. And yes, this might mean that kids have finished the game and there's like one person, probably the parent, that's still hitting that popper, waiting for that 4 or 5 to come out after like 100 rolls. That's just the way it is. Okay, so what is the probability needing to press the popper 4 or more times before 5 or 6 comes up? Okay, like I said, I'm sure this is a delightful game. So here's the idea, is the probability of 4 or more plus the probability of 1 to 3, right? That pretty much gives me all of the possibilities here. That has to equal to 1. Okay, so the probability that something happens plus the probability it didn't happen, that has to be 1. Okay, and it's very common. This is called rule of complements. Okay, it's a very common thing to do in statistics. Again, if you've taken, Math 1350, 1330, or whatever it was back in the day, Math 145, you would be acquainted with this rule. This happens pretty often. Okay, so what we want to do, okay, is saying, well, what is the probability of needing to press it 4 or more times before a 4 or 5? So that would be what's the probability of 1, 2, 3 plus probability of 4 plus is equal to 1. So we want to know about 4 plus. We're going to do this 1 minus probability of 1, 2, or 3. Okay, and that's going to be probability of 4 plus. Rather than add up 4, 5, 6, 7, ... We want to just figure out, like, well, instead of adding up all these, if I just add up probability of 1, 2, or 3, right? That's a pretty finite amount of things I have to add up. So let's do it that way. Okay. Now, Simplify your answer. Do not round until the final answer. I'll believe you this time, although last time I did this, it was, you know, it was a different rounding rule. Actually, it said this, it just was a different rounding rule, so we'll see. Okay, so same idea. We're just going to go, well, what's the probability of 1, 2, or 3? Okay, and the probability of this, and we're just going to sum these out when I'm done, okay? So, we wanted 1, 2, or 3, yeah? 4 or more, so yeah, 1, 2, or 3. So when I go to plug this in, okay, our probability was back to, right? Probability was back to 1/3, okay? So this P is equal to 1/3. All right, and then we're just going to write this down. P1 minus P, x to the minus 1, okay? And then so for the first one, we have 1/3, 1 minus 1/3, so that's going to be 2/3, right? 1 minus 1/3 would be 2/3. And then x being 1, so we have 1 minus 1, which is 0. So this is just going to be 1/3. Okay. Second one, 1/3. And again, 1 minus 1/3, right, should be 2/3. And we'd have 2 minus 1. 2 minus 1 is 1. So we have 1/3 times 2/3. Okay. And then for the last one, we have 1/3. Okay, this is 2/3, right? 1 minus P. And in this case, x is 3. So we have 3 minus 1. So that's 2. Okay, so this is 1/3 times 2/3 squared. Okay, 2/3 squared. So this is just 1/3. 1/3 times 2/3. Okay, and this is 1/3 times 4/9. Do you see how the 1/3 can be factored out? We could just, add these up this way. We won't, but you could take a little bit of a shortcut by saying, well, this is going to be 1, and then add this, and add this, and then multiply the 1/3 when we're done. Okay, so we'll just go through slowly. Okay, but we just have, actually, you know what? Screw that. You can just add fractions. That's okay. 1/3. This is 2/9, and this is going to be 4/27. Okay, I'm just multiplying these together. Now, I will go ahead and say, well, this is going to be 1 divided by 3 plus 2 divided by 9 plus 4 divided by 27. Double check to make sure I got all the things in here correctly. It looks like I do, equals. And then I'm going to go ahead and type this in. I'm going to say math fraction. There, it's 19/27. All right. Round to 4 decimal places. Very well. I mean, we have a very nice answer here, but they want 0.7037. Okay, so this is summing all of this up. This is 0.7037. Double check that. 7037. Okay, so let's see. 0.7037. Okay, fingers are crossed. Again, hopefully this time will be okay. They did not like that at all. What did they not like? Yeah. Oh, well, we'll just check it again. Huh. I wish I could see one before that. No, I wish I would have. I did forget to subtract it from 1. Oh, good Lord. So 1 minus 0.7037. Oh, how embarrassing. So there we go. 1 minus my previous answer. Okay, so now I'm getting 0.2963. 2963. All right, that should be the answer for us. That's what they ended up getting. That's why it was. So it's important to remember where you are in the problem. So you're taking account and getting all the little pieces, but that's what we got. Okay, I should have looked at this and said, oh, that adds up to 1. I should have just seen that, but I didn't. All right, so don't make that mistake. All right, and but that's how you do this kind of a problem. All right, so I hope that helped. I hope my mistakes did not throw you off track too badly, and we'll get to these and have our homework for this guy. Okay, so I'll send it. So thank you very much for tuning in here, and I hope this gives you some help. All right, thanks. Goodbye.